This is the AB Calculus review sheet for the chapter 7.1/7.2 Quest. The first question is asking us to first draw the region in between the two graphs y equals 2x and y equals x squared. So I drew the region below. Let me blow it up. Y equals 2x is the green line starting at the origin and having a slope of 2. And y equals x squared is the blue graph, and it starts at the origin and intersects the green line at the point 2, 4. So we know that these two graphs have points of intersection at 0, 0 and 2, 4. And then I shaded the area in between them, that pink color, and that is the area that we're going to find in part A. So the first thing that we would want to do is realize that we're going to be subtracting the bottom curve from the top curve. So we're going to integrate with respect to x. So that would be from 0 to 2, since those are our boundaries. And then we are going to do the top curve, which is 2x, minus the bottom curve, which is x squared, dx. And since we're not allowed to use a calculator on this one, we have to find the antiderivative, which would be 2x squared over 2 minus x cubed over 3. And we want to plug in a 2. So that would be 2 squared minus 2 cubed over 3, which would be 4 minus 8 thirds. 4 is really 12 thirds, so we would get 4 thirds units cubed, or I'm sorry, units squared, as the area of that region. For part B, we're asked to find the volume of a solid that would be created by creating cross sections perpendicular to the x-axis that have an area of the sine of pi over 2x. So if we already know the area of the cross sections, all we need to do to find the volume is multiply it by delta x. So we are going to take the integral from 0 to 2 of a of x times delta x, which would just be the sine of pi over 2x dx. And so now, without using our calculator, we would have to do a little u substitution to find the integral. So we would let u equal pi over 2x, du would equal pi over 2 dx. So to balance it out, we need to make a 2 over pi on the outside of our integral. And that is still from 0 to 2 sine u du. And the integral of the sine of u would be the negative cosine of u. So we have 2 over pi times the negative cosine of u, which is pi over 2x. And we want to evaluate that from 0 to 2. So we have 2 over pi, and we can pull out a negative, times the cosine of pi, if I plug in a 2, minus the cosine of 0, which would give me negative 2 over pi times negative 1 minus 1, which gives me an answer of 4 over pi. And since this is volume, it'd be units cubed. In part C, we are now given cross-sectional areas that are squares that are perpendicular to the y-axis. So since they're perpendicular to the y-axis, we need to change our equations and have them be in terms of y. So we have y equals 2x is going to become x equals 1/2 y. And y equals x squared will become x equals the square root of y. And if we imagine our figure, redraw it, if we have cross sections that are perpendicular to the y-axis, they'll be going horizontally across our figure. So we know that the side of one of our squares would be the right curve minus the left curve. That would be the distance between the two squares. This curve minus this curve would give us this distance. So that would be the square root of y minus 1/2 y. And so now if we wanted to find the area of that square, the two sides would have to be the same. So we would just square that. And then if we wanted to find the volume of that square, we would multiply it by delta y. So to find the volume of the solid, we would integrate, this time from 0 to 4, since we're integrating over y, of the square root of y, or y to the 1/2, minus 1/2 y, quantity squared, dy. Since you don't have to evaluate the volume of the solid, once you set up the integral, you are done with the problem. For problem number 2, we graphed f of x and g of x using the graphing calculator. And we first want to find the area of the bounded region. So before you find the area of the bounded region, it's very important to find the points of intersection so we know over what x values to integrate. And using the calculator, we can find that the 2 points of intersection are 0, 0, and 1.136, 1.764. So now that we have the graph and the points of intersection, we're ready to do the top curve minus the bottom curve to find the area of the shaded region. So we're going to integrate from 0 to 1.136. And the top curve is 1 plus sine 2x. And we're going to subtract the bottom curve, which is e to the x over 2 dx. And plugging that into our calculator should give us 0.429. And since this is area, that would be units squared. If we want to find the volume of this solid generated when we rotate it around the x-axis, so this line right here, first we need to recognize that this will be the washer method of finding the volume of the solid, since we will have a hole. And this will be our little radius r. Our big radius of the entire solid before the hole is subtracted out will go from f of x, 1 plus sine 2x, down to our axis of revolution, or y equals 0. So to find the volume, we are going to use the formula 0 to 1.136 of big R of x squared minus little r of x squared dx with a pi out in front. So to find big R of x, we know that it is the distance between f of x to our axis of revolution. So that'll just be 1 plus sine of 2x minus 0. And then our small radius, little r of x, will be the distance between our g of x, e to the x over 2, minus our axis of revolution, 0. So we're going to integrate from 0 to 1.136 of 1 plus the sine of 2x squared minus e to the x over 2 squared dx. And plugging that into our calculator should give us 1.358 pi if you did not multiply by the pi. Or if you did multiply by the pi, 4.2665 units cubed. What you can also do for this problem to make it a little bit easier is you can store 1 plus sine of 2x in for y1, and that could be your f of x. And then in for y2, you can store g of x. But since you only had to type these functions in one time, there is no need to store them. For the next set of questions, we're going to be using the following picture. We have an area that is bounded by y equals x squared, which is the purple line, y equals 1, which is the red line, and x equals 2, which is the green line. And so I'm just going to shade in that region right there. So the first thing we are going to do is calculate the volume of revolution if we were to rotate this figure around the x-axis. So I'm going to draw that in using, what color should I do that? In yellow. Or orange. For part C, we're going to rotate around the line y equals 1. So I just kind of redrew a sloppy little picture right here. And since the figure is actually on the line y equals 1, when we rotate it around, it will be the disk method instead of the washer method, since there will be no hole. So we are going to integrate in terms of x between 1 and 2 of just the big radius, which would be in between y equals x squared and the axis of symmetry, or I'm sorry, the axis of revolution, y equals 1. So we have x squared minus 1 as our distance, and that will be squared dx. So plugging that into our calculator, we will get 7.959 or 38 over 15 pi. And you can get 38 over 15 pi by just using math fraction. So just integrating this part and then using math frac and then tacking on pi to the end of your answer. In part D, we're going to rotate around x equals 2. So again, we need to have our equations in terms of y instead of in terms of x. So we have x equals the square root of y, and we already have x equals 2. So if we're going to rotate around x equals 2, we again will use the disk method since there will be no hole since our figure lies on x equals 2. So we'll just have this big radius right here. And to find that big radius, r of x, it is just the distance between 2 and the function, the square root of y. And you always subtract right minus left, just like we always subtract top minus bottom. So again, I want to integrate in terms of y, so we'll be integrating from 1 to 4 of 2 minus the square root of y squared dy. And if we type that into our calculator, we will get 2.618 units cubed. For question E, we are going to rotate around y equals 6. So you can see that this will be the washer method since we're going to have a pretty big hole in the middle. The big radius will be from 1 up to our axis of revolution, and our small radius will be from our function to the axis of revolution. So remember, we always go top minus bottom, and since our axis of revolution is on the top, to find our big R of x, we're going to say 6 minus the bottom boundary line, which is y equals 1. So 6 minus 1 is 5. And then to find our little r of x, we're going to say 6 minus our function, which is x squared. So to integrate, we're going to integrate from 1 to 2 of our big R of x, which is 5, so 5 squared, minus our little r of x, 6 minus x squared, quantity squared, dx. And typing that into the calculator will give us 33.929 units cubed. For question F, we are going to be rotating around the axis x equals 5. So again, we're going to have a pretty big hole, and this will be the washer method. So if I draw my radii, it looks like my small radius will be in between the line x equals 2, and my big radius will be in between the axis of revolution and my function. So to find my big radius, I'm going to need the function in terms of y, so that will be we always go right minus left, so that will be 5 minus the square root of y. And my little radius will be 5 minus 2. And then we need to integrate in terms of y, so we're going to integrate from 1 to 4. And we'll take our big R of x, so 5 minus the square root of y squared minus 3 squared dy. And (53/6 pi) units cubed. And I realized on the last one I made a mistake, and I can't erase it. That answer should be 54/5 pi units cubed. On the solution sheet, the integral was going from 1 to 6, but it should be going from 1 to 2. So I apologize for the earlier mistake. For the next problem, G, we're going to rotate our figure around y equals -2. So this will be the washer method since we will have a hole, and our hole will be in between y equals 1 and our axis of revolution. and our big radius will be in between our function and our axis of revolution. So we will be integrating from, this time in terms of x, 1 to 2, pi out in front, always forgetting that. And our big R of x will be our function, x squared, minus our axis of revolution, so minus a negative 2. And our little r of x will be 1 minus a negative 2. So we will have x squared plus 2 quantity squared minus 3 squared dx. And plugging that into our calculator, we should get 33.591 units cubed. If you're having trouble plugging these into your calculator, a good idea might be to store r of x in for y1 and store little r of x in for y2. And then when you do the integral, you can just integrate from 1 to 2 of y1 squared minus y2 squared dx. That might work better for you if you're having trouble plugging in the correct parentheses. In this problem, we have a region that's bounded by the following graphs. Y equals the square root of x, which is the purple graph. Y equals 2, the blue graph. Y equals negative x squared plus 2, which is the yellow graph. And x equals 0, which is the green graph. So our region would be this area right in here. So first we want to rotate this area along the x-axis. So we have our axis of revolution right here. So this will definitely be a washer type of problem. And we're actually going to have two small radiuses if we rotate around the x-axis. We can see that we would have a hole between the square root of x and our axis of revolution, so that would be a small r. And we would have a different hole between negative x squared plus 2. And then our big R would be between the line y equals 2 and our axis of revolution. So we actually need to do two separate integrals to help us find our volume of revolution. And this would be broken up between the boundaries 0 and 1, and then again from 1 to 4. So we would have to set up two equations. Big R of x would be from 2 to 0, so it would just be 2. Our first little r of x, so we can do r1 of x, would be from negative x squared plus 2 to 0, so just negative x squared plus 2 minus 0. And then our little r would, our other little r would be from the square root of x to 0. So it's just the square root of x. So our two separate integrals would be pi. And we would go from, this would be a good time actually to store these equations in y1 and y2. So you can make negative x squared plus 2 your y1, and you can make the square root of x your y2. So we're going to take the integral from 0 to 1 of 2 squared minus our first r, which is our y1, dx. And then we're going to add the integral from 1 to 4 of 2 squared minus y2, I'll just leave that guy there, minus y2 squared dx. And if we put that all into the calculator, we will get 14.765 units cubed. Now we're going to rotate our figure around the line y equals 2. So luckily we do not need to use the washer method here since we're going to be rotating around our line that our figure is already bounded by. However, we do need to do two separate integrals again since our curves are different. Between 0 and 1, our big R is going to be in between the function, or the two functions, 2, the top curve, minus the bottom curve, which is, in this case, y1. And that entire thing squared, since we're just doing the area of the top minus the bottom. And then the integral from 1 to 4 of the top curve minus the bottom curve, which is y2 squared dx. And putting that into our calculator would give us 1.0333 pi. If we are going to rotate around the y-axis, we now need to get our equations in terms of y instead of in terms of x. So our first equation will turn into y squared equals x. And then our third equation will turn into negative y plus 2, the square root of that. So subtract the 2, multiply through by the negative, and then we have x equals 0. So if we are going to be rotating around the y-axis, again, we have to set up two separate integrals because we're going to have two different, actually it looks like we will only have one hole going on. So our small radius, let's draw this out here so we can kind of see it. So it looks like our small radius will be in between our yellow function, which is the square root of negative y plus 2, and our big radius will be in between our purple function, which is y squared equals x. And we'll just have one hole, so we only need to set up one integral. And we're going to integrate with respect to y, and this shaded region is in between 1 and 2. And the big radius, I'll write it over here, will just be y squared minus 0, so y squared, and we always do right minus left. And our little radius will be the square root of negative y plus 2. So we have y squared squared minus the square root of negative y plus 2 squared dy. And when we plug that into our calculator, we should get 17.907 units cubed. If we're going to rotate around x equals negative 3, thankfully we have the same situation. We only need to set up one integral since we will only have one hole. So we'll go from 1 to 2. This time my big radius will be in between my purple function and all the way out to x equals -3. So that will be y squared minus a -3, or plus 3, quantity squared. And then my small radius will be the square root of, easier to write, 2 minus y probably, minus a -3, so plus 3 squared dy. And putting that into our calculator should give us 15.699 pi units cubed. In the last part of this problem, we're going to be finding the volume of a solid that has this region as a base, and the cross sections of this solid are going to be rectangles that are perpendicular to the y-axis. So the base of my rectangle will be going this way, perpendicular. So to find the base of the rectangle, I am going to do the right curve minus the left curve. And this does need to be in terms of y. So my right curve is y squared. And my left curve is the square root of 2 minus y. So my side of my rectangle is going to be y squared minus the square root of 2 minus y. And so now if I know that that is the side of my rectangle and the height of my rectangle is 3 times the base, the height is going to be 3 times y squared minus the square root of 2 minus y. The width of my rectangle will just be dy. So to find the volume, to find the volume of the solid, I'm going to integrate with respect to y. So from 1 to 2 of 3 times y squared minus the square root of 2 minus y. And we could just say that that is squared since we're multiplying it together, dy. And if we put that in our calculator, we get a volume of 11.986 units cubed.